Let's try to understand a little better how uniform cost search works. We start at a start state, and then we start expanding out from there, looking at different paths. And what we end up doing is expanding in terms of contours, like on a topological map, where first we span out to a certain distance, then to a farther distance, and then to a farther distance. Now, at some point, we meet up with a goal. Let's say the goal is here. Now, we've found a path from the start to the goal. But notice that the search really wasn't directed at any way towards the goal. It was expanding out everywhere in the space. And depending on where the goal is, we should expect to have to explore half of the space on average before we find the goal. If the space is small, that can be fine. But when spaces are large, that won't get us to the goal fast enough. Unfortunately, there's really nothing we can do with what we know to do better than that. And so, if we want to improve, if we want to be able to find the goal faster, we're going to have to add more knowledge.
At the center of this page, it shows a starting state labeled S, and there are 3 circles with different radii enclosing S. A goal state is on the largest circle. There is a path connecting the starting state and the goal state.
The type of knowledge that's proven most useful in search is an estimate of the distance from the start state to the goal. So let's say we're dealing with a route finding problem, and we can move in any direction, in up or down, right or left. And we'll take as our estimate the straight line distance between a state and a goal. And we'll try to use that estimate to find our way to the goal fastest. Now, an algorithm called Greedy Best First Search does exactly that. It expands first the path that's closest to the goal according to the estimate. So what do the contours look like in this approach? Well, we start here and then we look at all the neighboring states, and the ones that appear to be closest to the goal we would expand first. So we start expanding like this, and like this, and like this, and like this. And that would lead us directly to the goal. So now, instead of exploring whole circles that go out everywhere in the search space, our search is directed towards the goal. In this case, it gets us immediately towards the goal, but that won't always be the case if there are obstacles along the way.
The title of this page is Greedy Best First Search. The starting state S is on the left, and the goal state G is on the right. The searching contours are a sequence of ellipses enclosing S rather than the uniform circles before.
Consider this search space. We have a start state and a goal, and there's an impassable barrier. Now, Greedy Best First Search will start expanding out as before, trying to get towards the goal. And when it reaches the barrier, what will it do next? Well, it will try to increase along a path that's getting closer and closer to the goal. So it won't consider going back this way, which is farther from the goal. Rather, it will continue expanding out along these lines, which always get closer and closer to the goal. And eventually it will find its way towards the goal. So it does find a path, and it does it by expanding a small number of nodes, but it's willing to accept a path which is longer than other paths. Now, if we had explored in the other direction, we could have found a much simpler path, a much shorter path, by just hopping over the barrier and then going directly to the goal. But Greedy Best First Search wouldn't have done that, because that would have involved getting to this point, which is this distance from the goal, and then considering states which were farther from the goal. What we would really like is an algorithm that combines the best parts of greedy search, which explores a small number of nodes in many cases, and uniform cost search, which is guaranteed to find the shortest path. We'll show how to do that next using an algorithm called the A-star algorithm.
The starting state S is on the left and the goal state G is on the right. There is a U-shaped barrier between S and G. If we are using the greedy best first search, when the contour hits the barrier, the algorithm will walk along the U-shaped barrier to the bottom and then to the right, and then reach the goal from the right side. But in fact, when the contour hits the barrier, if the algorithm moves up a little bit, it will reach the goal with a shorter path.